going to turn it over to Sister Jean and ask you to talk about the discipline of math. What does it mean? What is the perspective that mathematicians carry around about how they see the world?
There's a good reason why, if you go back to the original several liberal arts, that some of the top four were basically mathematical. Because mathematicians actually put the basis in what we now refer to as critical thinking. Going very, very far back, 2,300 years ago, Euclid wrote a book. It had 13 chapters in it, and it's called The Elements. That is, besides the Bible, the most written, the most printed book, the most copied book, and it is still used today in schools in modified form, of course. Well, what is it? It's the geometry textbook. Okay. Well, what did Euclid do that's so important that we are still using exactly what he did back then? What he did was, and this is kind of one of the bases of how mathematicians think, he put mathematics on what we call a footing of being an axiomatic system. In that we have several basic rules. You would think them as rules of the game, and then after you state those little rules, then everything else needs to be proved. Okay? So you have to show logically why, from the definitions and from the axioms or from previous theorems, what you're saying is true. Now, if you remember your high school geometry, you might remember writing proofs. Okay? And basically what you were doing is you were taking some given information and knowing what you knew about the given information and making inferences about it and then quoting theorems that backed up your inferences and then stating, aha, therefore we know this is true. Everything that mathematicians do, we always put on a basis of having a rational proof behind it. Big difference between the sciences and mathematics. Once we have proven the theorem, it's true. Period. End of sentence. The scientists are going to tell you something a little bit different about the way they work. Okay? But not mathematics. You know, what are we interested in? We are interested in seeing patterns. We're interested in seeing what's going on behind things. We're interested in seeing patterns in how numbers work. We're interested in seeing in patterns how gravity works. We're interested in seeing patterns in how fast things go and how rates of change and how what happens when you roll dice a lot of times and what happens when you flip coins and what happens when you look at a whole set of data of how people have gotten sick from certain things. And we look for patterns in everything. And then we make statements about those patterns, and then we say, I wonder if this pattern is always going to hold. And then, of course, we abstract out from those patterns and start thinking about what's the pattern telling us. And so then we start doing a proof. We like proofs. We like proofs a lot. In fact, if you take an upper-level math course, you will be writing proofs daily. Okay, why do we like proofs? Because once we've proven it, it's true. Mathematicians like truth. Now, one of the difficulties is that when you're working with things that are nice and hands-on, you know, you can actually see what's going on. You can actually feel what's going on. As soon as you start working with the patterns, you're abstracting out a level. And then sometimes people accuse us of being so abstract that we're sort of on the other side of the solar system heading out toward some nebula someplace, way beyond everybody else. Too far out, too far out. Well, yeah, we are. So, you know, you might want to think about some of these things. What do we think about? We think about, well, you know, we know that there's an infinite number of numbers, because if you start counting, you know, any number I would say, you could give me a bigger one, right? Okay, and that's just counting numbers. Then we take into account the fact that in between every one of our counting numbers, we've got all these wonderful things like halves and fourths and thirds and all those fractions. One of the interesting things we come up with in geometry is the fact that in between all those fractions, we also have other numbers that we can't describe as fractions. And where do they show up? They show up in diagonals of squares. Then we start thinking, us mathematicians, we start thinking, well, you know, we've got counting numbers, and we know that there's an infinite number of those, and we've got fractions, and we know there's an infinite number of those. Are there the same number of fractions as there are counting numbers? Turns out that there are. Then, when we start talking about all these numbers that fit in between, it's like, are they the same number? It turns out that there's not. There are more. And so we end up with different sizes of infinity. You see what I mean about us getting abstract? Okay? But this is the kind of thing that we think about. We're very interested in what's going on here. What's the pattern telling us? What are we looking for? One of the things that annoys the scientists is that we come up with these wonderful abstract ideas. We've proved them. We know that the abstract ideas are true. And then all of a sudden the scientists realize, you know, what they're doing over there actually describes how this kind of crystal works. That's not fair. Why do those mathematicians describe what's happening in real life when they're sitting in their ivory towers thinking from here up, doing all these wonderful proofs that are totally abstract, and all of a sudden it applies to chemicals. It applies to what's going on in the computer industry. Little fact. One of the reasons why computer encryptation actually works is because it's based on not being able to factor a huge product of two huge prime numbers. Yeah. You learned about prime numbers in grade school, right? Okay. Why are they so interesting? Well, you know, who knew that eventually the whole idea of taking two prime numbers and multiplying them together was going to give us a basis for encrypting the signals that we send over the airwaves by way of electromagnetism? Well, we came up with it, and then it got used. So this is the kind of thing that happens all the time in mathematics. Things that we think of certainly turn out to be very interesting a little bit later on. One of our famous mathematicians of the early 20th century is famous for having said that he was very happy that he was a mathematician because what he was doing was absolutely totally useless. And then a lot of the things that he's known for in mathematics ended up being the basis of a lot of what's going on in the computer industry as far as computer graphics is concerned. So it's not that useless. Okay? How do we make computer graphics look more like life? How do we get things on the computer to actually look like what's going on? Anybody in here remember the old Apple IIs? Graphics on the Apple IIs, they were blacks. And you kind of could see what the heck they were supposed to be. And then things got better and you had more resolution and the blocks got smaller. And now you look at it and they're practically picture quality. And what's behind all that? Math is on the basis of all of that good stuff. And all the computer's doing is working with zeros and ones. And how does it know all that good stuff? That's a good question. Because we proved that things are true in all of our logical stuff. Anyone in here do Sudoku? One of the things that's good about Sudoku puzzles is that it's a deeply mathematical construct in that when you're putting the things in the position, they're numbers, yeah, but they're not numbers like you're adding them together. You're thinking about, because of certain ways that patterns fit together, the only number that can possibly fit in this block is this particular number. Okay? So you're using logic. And a lot of the thinking that goes behind that is the kind of thing that mathematicians think about a lot. In fact, if we were going to say that, you know how musicians have to do their exercises and play their scales, and singers sing up scales and down scales, the kind of things that a mathematician would do to do the same thing would be working Sudoku puzzles. It's the kind of thing that we do to keep our minds thinking about that kind of stuff in logic. Okay?
With what you had described, that was all mathematically related. Now, with your vision of the world, do you feel like in everything that you look at, you're always looking for those patterns with every single thing? And another question, not related, but, you know, in our society, I think a lot of young students are shying away, at least in America, from, you know, math and the science fields. What's your take on that, I guess? What's your opinion on that?
Well, I have a deep bias against standardized testing. And part of my problem with standardized testing is high scores might tell you something, low scores tell you nothing, because you don't know why the student got the low score. The other thing I have against standardized tests is they're very constrained. There's no room for creative thought. You know, it's like you're stuck in this standard mindset of things. You know, you've got to have this and everything is factual. So a lot of people come out of schooling convinced that mathematics is a bunch of rules that they have to memorize, and that's it. That's all there is to it. And who wants to go into that? I mean, that's not fun. Now, if you go downstairs to either room 117 or 118 and look at the bulletin boards, you will see things that my Math 130 and 131 class have done. And it will look like a beginning art class, because what we've done is we have done coloring and we've done putting together patterns that are visual, just to see what would happen if we arrange things. Like, for example, quilt blocks. If you take quilt blocks and you have a certain symmetry in the quilt block and a certain arrangement of the way you've got your figures in the quilt block, and then you put 4 of them together, because of the way that the colors go together, you see a totally different pattern come out. And so we explore that kind of thing. I think if they did more of that, if they had more time to do that down in the grades, the kids would be more excited about it, and then maybe people would like math more. That's one of the things I preach to my students. So.
At what age did you discover your passion for math, and was there anyone in your family that, like your parents?
I would say probably when I was my very first tutor job was when I was in kindergarten. I'm the leading edge of the baby boom, okay? And somehow demographics didn't get followed, and so people didn't realize that when we turned 5, that there was going to be this huge number of more kids in kindergarten, so our classes were too big. There was a boy in my class who could not count past 20. He just couldn't. He couldn't get past 20. And the teacher just had too many kids to work with, so she decided, since I could count as far as you wanted, she put him in the corner with me. And so we had this discussion, and this was what his problem was. When you started counting, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the next one was 10, and then the next number was 11, and then there was 12, and there was all these special words, okay, 15 and 16 and 17 and 18 and 19 and 20. And you know, these adults were telling him that the one that was one bigger than 20 was 21, and that wasn't a special word, that needed to be a special word. And the adults were not telling him the special words. And you know, they had lied to him about Santa Claus, and they had lied to him about the Easter Bunny, and therefore, they were probably lying and laughing at him. Well, he believed me, we got over his problem real fast. But I think that might have been where I kind of discovered.
I think it was Piaget that said about kids understanding the number being an actual physical something. It's something. Do you think that you understood that at 5? That it represented a number?
Remember sitting in a corner with a piece of paper and just doubling numbers until they got really, really big. And then doing the same thing with making numbers 3 times bigger.
Did that at what age?
I think I was in 1st grade.
So that was your fascination right there.
Looking for patterns and